Come on in, everybody. Come on, people now. Cry for your brother. I don't know the words. Oh, well. Anyone have any questions while we're waiting for people to come in? Still got about a minute before class is supposed to start, and we only have about 9 of our people in here so far.
If I need to view a recorded meeting after the fact, where would I go?
You go to my YouTube channel.
Okay.
In fact, if you subscribe, it'll give you an email each time that I post something new. And if you look in the actual comment section, it'll show you whether it's a 241 or a 242 course, because it'll say PHY 242 or PHY 241. And since you are 241, obviously you want to look for those. But I posted Monday night video there.
Okay. Second follow-up question is attendance recorded during these Zooms?
Yeah, it actually Zoom does it for me, so I can just always pull it up and see when you got here. The thing is that it only reports whatever name you use up there. So if you guys are really not wanting your name to ever appear on my YouTube channel, you need to email me, let me know that so I can stop it. And then you can start like using a different name, but you need to let me know what that name is, so I'll know that I'm not accidentally, counting the wrong person for being absent or whatever.
Okay. So the reason I'm asking that is my stomach is like in knots right now.
Gotcha.
So I don't know how much longer I'm going to make it, but I'm going to kind of stick through it. So I just asked that up beforehand.
Well, I happen to be so awesome that I've been known to cure ailments. So there's a good chance that just watching me will make you feel better.
All right, we'll see what happens.
Good luck with that.
All right,
right?
All right, thanks.
No problem. Yeah, this will all be recorded. It should be posted tonight unless the internet goes really, really slow or something, and that does sometimes happen. But anyways, it should be posted tonight.
I have a question.
Yes, ma'am.
So for the textbook, I need a course ID number or a program ID.
Yeah, so that is if you're trying to get into MyLab and mastering from the internet. If you're going through Canvas, you don't want the course number, because you will actually force yourself to not allow me to see the grades that way. So what you do, the way I've got it set up, is called a deep integration. So you just go into Canvas and click on homework 1, for instance, and it'll ask you to make an account. And at that point, you can either pay for it or put in your user code that you've already bought, and it'll give it to you.
And you said click on which one?
If you go into week 1 module, you'll see there's chapter 01 homework. You can click there, and it's if you haven't already signed up, it's going to ask you to go ahead and sign up there.
Thank you.
No problem. And that is a place where you can actually purchase the book there. They're offering you the $79.99 version without the e-text. I was told they're not doing that anymore, so it might not even work, but you need the book, so don't take that one. That being said, I think it's $129.99 with the ebook, and that should be cheaper than if you bought it from the student store, but I don't know how much cheaper. If someone knows, let me know. That would be helpful. And you get 2 weeks free, so you don't have to actually pay for it right now. 2 weeks from Monday basically is the free window, and if it ends up that you decide not to take a class or something, then you wouldn't have wasted that money. That being said, no one ever drops a class, so I hope that's the case this time too. Is it Darnisha? Yes, ma'am. You can shake your head.
Yes, Darnisha, I'm sorry, I was muted.
No problem. Anybody else have any questions? All right, so last time I pretty much only talked a little bit about the atomic theory. I think I might have mentioned something about a poop, which is kind of funny. That makes me laugh because I am perpetually in 3rd grade. So you'll notice everything about me is making funny jokes. Like, I think last night I said the phrase do, whatever they do, and then I started giggling. So that's going to happen. But anyways, we're going to try to continue on as if I'm not that goober, but I am going to be that goober. If I aggravate you, send me an email, let me know. I'll try to straighten up. But anyways, we did cover the syllabus to some extent, and you can see that on the Monday's video. And then I talked to you about how atoms, oh no, I didn't do the atoms. That was in 242. After that, I pretty much didn't talk to you about anything subject wise, but I'm going to now. And I have my iPad that I can use to show you the notes. So we're going to start off in chapter 1. And to be honest with you, I can get through enough of chapter 1 for you to complete the homework, especially if you take the time to go up and watch. There's a video on my week 1 module. It says sig figs, scientific notation, units, and dimensional analysis. The units and dimensional analysis is the only part I might not get to tonight. So you can actually watch that and figure out by yourself what it is. But what I'm going to do is I'm going to make the homework for this chapter 1, not do Sunday, but rather do Tuesday. So that gives you an extra day, because I'm going to work at least 1 or 2 examples next time if I don't get to it tonight. Okay. All right, we've got 16 of you guys in here, and remember my phrase guys just means something for you people. Okay, so I will I'm not referring to any kind of gender on that situation, but I'm going to turn on my iPad and I'm going to give you some introductions, specifically chapter 1 of your book. I'm going to go ahead and pull that up right now. Just so I can read to you exactly what the topics are and what the name of the chapter is and that sort of stuff. And I'm basically just giving you that so you understand what's important for this particular chapter. It's sort of a boilerplate chapter where they teach you sort of all the stuff you need to know. And a lot of it, they sort of expect you to know. So for instance, I'm not going to take time to teach you about scientific notation, but if you're not comfortable with scientific notation, if you can't readily look at a number in scientific notation and tell me what it is in regular notation, move the decimal, in other words, or if you can't do the opposite, which is take a number in regular notation and make it scientific notation, then that's going to be a problem. So feel free to meet me during office hours. There's an office hour that I always do right after this class, for instance. Also, I have a 242 class that runs from 5:20 to 6:40 on Tuesdays and Thursdays. You can log in as early as 6:35, just in case I accidentally or I let students out early, which I never do, but that'll keep you from missing me, in other words. So if you sign in at 6:35 and wait till the class is over, then you can ask questions about 241 or anything else you have. So that's another office hour. I put that the invitation to that particular meeting up at the top in the second module in Canvas. So you now have access to that. Now, what I did is I did it for basically both this class and for the other class. So you'll see another invitation to this class in here, even though you already had that. But it's just a lot easier to copy all of it to everywhere instead of just picking out each one. So feel free to use that as an office hour. You can also come to campus. I have an office hour before my 9 a.m. class on Mondays and Wednesdays. I have an office half hour from 8 to 8:30 before my classes on Tuesday and Thursday. And I also have office hours during my lab, specifically meaning after the first hour of lab, I'm pretty much just floating around helping students, and I have some free time. So that's a good time for you to ask questions. So if you have any problems that you don't know about scientific notation and stuff like that, feel free to come ask me. I want to help you. So even if there's something you don't know about and something that quote unquote supposed to already know, that's okay. I can help you. Okay. So just let me know if you need any of that. I'm going to jump right in talking about the Systems Internationale, which is the technical name for what you guys probably call the metric system. We in physics refer to 2 of them. We refer to the CGS system, which is sort of the old version of the of the Systems Internationale. That was when we were using the centimeter for the base unit of length, and the gram for the base unit of mass, and the second for the base unit of time. Whereas we now use the MKS system, which is the meter kilogram second system. Okay. both of those are more or less the metric system. And it's a rational system of units where instead of having something goofy like what I'm getting ready to show you, there's something called the G-man, or at least that's what I call it, that we use to try to make sense of a particular set of units. And when you have something that absurd that you have to put in your memory to help, then that's an indicator that the unit system you're working is not very good. So let me start off by go ahead and sharing my screen. I'm going to create a new document. Oops. Let's see. New one, new notebook. I'm going to call this PHY. This is 241 D01B, and today's date. Oops, that is not what I meant to do. And today's date. Oh, yep, it definitely copied the word days there. I'm going to put an underscore after PHY 241D02B. Your section number really is supposed to be N01B, but we typed it in wrong, so I apologize for that. But at the end of it, it's underscore 08232023. So that's the little code that you'll see in the comment section, or excuse me, in the details section of my YouTube channel. And that's what you can use when you go into Google Docs to find the actual notes for that particular page. So just keep that in mind. I'm going to do this and say copy page. Now I'm going to say paste page. Paste page. Sorry, it's taking a little bit of time here. My wife is cooking something that smells really delicious, and now I'm not functioning properly. It's a fat man curse. Good now. So again, I'm trying to share this with you, but I first got to make the document so that it's something you can see. I think I've done that now. That's right. Let's get rid of this page. That's not it. So move page to trash. There you go. All right, so I got that. Now I'm going to do share screen, and hopefully it will work. Share screen. I'm going to do iPad, and it does this every week. It tells me to download something, which I've downloaded every week, but I'll wait for it to do that. Normally it doesn't take this long, but okay, it looks like it's attempting to function properly. Now I got to turn this on. And that should cause it to be visible. Yeah, there it is. Okay, finally, it's there. So, and that's my link up at the top. You can see that that's what my YouTube channel address is. So the first thing I want to talk to you about is we're using a system of units called the System International, and it's supposed to be a rational set of units as compared to, let me write this ginormous symbol. And this isn't even the whole thing. Really, if I wanted to finish this, then I'd put 2 C's in each of the P's, and then I'd put 8 O's in each of the C's. So anybody recognize what that is? Okay, so this is a little mnemonic you can use to help you remember basically what the units of a gallon are. So 1 gallon is 4 quarts. That's why you see the 4 Q's. Each quart is 2 pints. That's why you see the 2 P's. Each pint is 2 cups. That's why you would normally see 2 C's in there. And then each cup is 8 ounces. So that's why you would normally see 8 O's inside of the C, right? So that's a really unfortunate thing, because if you really want to do any work with converting back and forth between cups and pints and quarts and gallons and all that stuff, you've got to know all these facts. Whereas in the SI system, you really just have to realize that each conversion is like a factor of 10 away. It's either a factor of 10, a factor of 10 squared, a factor of 10 cubed, a factor of 10 to the 6th, a factor of 10 to the 9th, or 10 to the negative 6, or 10 to the negative 9th, and that sort of thing. But this one, really being able to convert units and knowing this kind of thing is actually allows you to relieve yourself of a tax on mathematical ignorance, basically. So for instance, if you have a weed eater or a chainsaw or something like that, you'll know that they actually require you to mix the oil with the gas, and then you'll go to Lowe's or Home Depot, and in doing that, they'll sell these little containers, very specific amount of oil, and it's like exactly the amount of oil that you're supposed to use if you're using, say, 50-to-1 ratio and using 1 gallon of gas. And the markup on that is like 700%. So it's literally like a tax on your lack of knowledge. That's why I said ignorance, your lack of knowledge about math, or your lack of knowledge about unit conversions. What this particular diagram does for you is you can go through and figure it out that ultimately 1 gallon is equal to 128 ounces. And then once you learn the methods of unit conversion that I'll be teaching you in tonight, then you can use that to basically measure out your own oil to put into your gas. And you can just buy regular quart oil, or even 5 quarts of oil, which is way cheaper than buying even a single quart of oil. But those little bottles literally is sort of equivalent to paying like, $8 or $9 for a quart of oil, and that's not reasonable. Okay, so with that in mind, I'm going to give you the SI prefixes. And to be honest with you, if you're going to be a scientist or an engineer, at least in, let's say, chemistry, physics, astronomy, astrophysics, or any of the engineering branches, they sort of expect you to know some of these prefixes. That being said, in engineering, they don't use the SI. Okay, they use some, at least in America here, they still use pounds, or what we call the British system. But anyways, you should know from nano all the way up to, say, giga. That would be acceptable. But I have created myself a mnemonic for the prefixes, but the mnemonic is mnemonic that I use is quite childish, so I will refrain from sharing it with you, but I'll get you started. So basically what it is there is a T, and then a dot dot, and then a G, and then a dot dot, and then an M dot dot. So I'll give you part of the mnemonic, and then I'll suggest, hey, you make up your own. In fact, if you turn one in and it's good, I'll even give you extra credit. Okay, so I say the great monarch dot dot King Henry died. Now I say the word by, but that right there is the base unit. And the base unit for the System International is supposed to be, technically the base unit is the kilogram for mass, but you can tell the kilogram already has a prefix on it, so we don't use like kilogram. So it really is okay to just say G here. But when you use an equation in this class that calls for mass, you're supposed to use kilogram there. That's what I mean by saying that's the base unit. So a gram, a meter, a second. So mass, length, and time are the most critical variables to science. So that's why I put those 3 there. There's other units. For instance, there's a unit for current, which is the ampere. There's a unit for charge, which is the coulomb. The unit for electric potential energy, which is joules, or the unit for just potential, or just electric potential, and that's the volt. So those are bases as well, and you can put the prefixes on it. But after the base unit, it goes died. So the great monarch King Henry died by drinking chocolate milk dot dot, and I'm not going to give you the rest, but basically this is the Greek letter mu, and then dot, dot, N, and then dot, dot, and then P, okay? So this is tera. This is giga, or if you watch Back to the Future, giga, okay? This is mega, as in megamind. This is kilo. This is hecto. This is deca. Again, that's the base. This is deci, which if you are in the medical field, or if you're old enough to have a wife that's had a child, or old enough to be a woman that's had a child, you also have heard of the term called sonometer. And a sonometer is also the same thing as a decimeter. It's 1/10 of a meter. Actually, yeah, I think that's what it was. It's either that or a centimeter, but that you can trace that back. So the next one is centi, and that should make sense because how many cents are in a dollar? Anybody? 100, right? And it turns out, yeah, and it turns out that the centi is in fact 1/100th of a meter. So if you had a centimeter, that would mean 1/100th of a meter. Then the next one is milli, and then this is micro, and this is nano, as in nanobots and stuff like that. And this one's pico. Okay. Now, what makes this a rational system of units, and in fact is somewhat of a, the whole idea of the SI is a little bit of a Renaissance idea. And that's when we sort of did it. It was actually under Napoleon, and shortly thereafter, the System International, which is obviously sounds like French, and it is French because it was spearheaded by the French. That was a rational system of units because we were in the age of enlightenment. So what it is the base unit goes here in this line, and that's basically no prefix, and no prefix would mean 10 to the 0 power. I will remind you that anything other than 0 raised to the 0 power is 1. So there's basically just the base. So a gram is a base, a meter's a base, a second's a base, a volt's a base, all that sort of stuff. Now, if you go to the left, that's 10 to the 1, and that means 1 deca refers to 10. And 1 hecto refers to 100, and 1 kilo refers to 1,000. Now, notice I've got a dot and a dot. We don't go in increments of power of 10 for all of them. In fact, from the base, we go a power of 10, power of 10, power of 10 to the left, which is getting bigger. And then to the right, we go a power of 10, a power of 10, a power of 10, which is getting smaller. But then we skip to 3 powers of 10. So this one would be 10 to the 6th, or a million. So a mega dollar is $1 million. A gigadollar is $1 billion. And then a teradollar is in fact $1 million. Okay. If we go the other way, the same thing happens. That's 10 to the -1, 10 to the -2. Now you can see it's 1/100th, 10 to the -3, 10 to the -6 again. So notice it went to 6 again. 10 to the -9, and 10 to the -12. These are the prefixes that you use. And when we go to use that, you can actually use it as it is right now. It's not fast, so it's not really good, but this is the kind of thing that I would give a biology student who doesn't do a lot of math, but needs to know those units. It's also what I give to my conceptual physics, which is supposed to be a fairly non-mathematical physics. So for instance, if I said, hey, I would like to know how many nanograms are in this number, this is how you could do it. You could say, let's say I have a number 0.000. Notice I'm grouping that in pods of 3. Please do that with anything you turn into me. Put it in pods of 3. I don't care if you start it right. So it's, to the left of the decimal is 3, and then another 3, and then another 3. If you started at the far left-hand side, as long as it's in groups of 3, that makes it easier for me to count. But I'm going to do 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 91. and let's call this gigagrams, and I want to convert it to nanograms. Okay, this is what I do. Okay, I am going to start on the prefix that I have, which is right here. Okay, and I'm not going to count the spots. I'm going to count the moves. That's the important thing here. You've got to pay attention to the number of moves you make, not the number of places you were. And you got to pay attention to which way you go. So if I want to go from capital G to lowercase n, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice I did count the base. 10, 11, 12, 13, 14, 15, 16, 17, 18. So I went 18 decimal places and I went to the right. So that's what I got to do here. This would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So in fact, the answer is 91000 nanograms. And of course, if I gave you something in picograms, for instance, and asked you to go to mega, then you'd obviously, you see the decimal place would move to the left, which is exactly what you do. And you could still count the number of moves. So again, remember, I'm counting the moves. So count moves, not spots. Okay. Now, that being said, as a calculus-based physics student, and even really as an algebra-based physics student, so if someone's taking a 201 or 202 course at TCC, I do not recommend this method. This can be used occasionally, but the main thing is by knowing this mnemonic or knowing a mnemonic in this order, you now can figure out exactly what power each prefix means. So this literally means, hey, a kilo means 10 to the third of the bases. Mega means 10 to the sixth of the bases. So another way I could convert that is I could say 9.1. Here's another example. This was an example too. So I could say, actually, let's do it. I'll do the backwards way this time. Let me kill this. I'm going to start with the number we ended up with. So I'm going to say 9.1 times 10 to the 4 nanograms. If I wish to convert this to, let's say teragrams this time. So I want to convert it to teragrams. Okay. This is how I do it without using this cumbersome moves and counting and left and right stuff. What I'm going to do is I'm going to take my nanogram and I'll say 9.1 times 10 to the 4th nanograms. And in converting units, the trick is this. Look, you have a number and there's mathematical operations you can do to a number, but there's a limited number of operations that are mathematical that you can do to a number that don't change its value. So for instance, you can take a number and you can multiply it by 1 and you won't change its value. You can take a number and divide it by 1 and that won't change its value. You can take a number and add 0 to it, that won't change its value. And you can take a number and subtract 0 from it and that won't change its value. Well, those last two are not very helpful, but that first one or second one, depending on how you want to think about it, are good ways of thinking about it. So we're going to multiply by 1 in such a way that the unit we have disappears and a unit that we want replaces it. The key then is to understand that 1 can be written a lot of different ways. You can write 1 as 2 over 2 or pi over pi, or you can write it as, for instance, 1 foot over 12 inches, or you can even write it as 12 inches over 1 foot. the main thing is you see that as long as the numerator is physically equal to the denominator, then that value is as good as 1. So in this case, I want to get rid of nanograms. So the first thing I'm going to do is I realize I'm multiplying fractions here. And though you guys have completed at least Calculus 1 to take this class, I'm sure you still make the occasional arithmetic error, especially when dealing with fractions, or at least most people do. I happen to love fractions, but I make horrible mistakes with decimals. So that gets you off the hook a little bit. You can say, okay, well, Mr. Younger makes mistakes too, right? So what I'm going to do is I'm going to try to get rid of nanograms. And just like if I was trying to do 4x cubed divided by 3x, you know what happens there. That becomes 4 over 3. And then the x cubed up the top at the top cancels out with one of the x's in the bottom and leaves x squared. So if you think about it that way, and then you make the conclusion that really when you say a number is like $1 million, the unit of dollars or the unit of $1 million is multiplied by the 1. Okay, just like the x cubed is multiplied by the 4. So if you have it such that you're multiplying a unit by something that has the same unit in the denominator, then those two units can cancel out. So that tells me right now I need to multiply by this by 1 in such a way that the nanogram is in the bottom. So I look up and I look at the lowercase n and I see that's 10 to the negative 9. And what that means is 1 nanogram is 10 to the negative 9 grams. Notice how I went to the base. Now, in doing that, one thing that helps me is in terms of keeping track of what I've done is I use a special symbol to cancel out them, and I change the symbol each time. So right now I'm going to say this nanogram canceled out with this nanogram, and I'm going to do it by drawing a slash from the top left to the bottom right. You'll see more chances later. Now I've converted from nanograms to grams, but I really wanted nanograms to teragrams, so I've got to do yet another step. So I'm going to put another fraction here. And this time, I now have grams, but I want to get rid of grams. So I need a gram in the bottom. And in fact, I want a teragram at the top. Now, if I look, a teragram is supposed to be 10 to the 9th grams. So what that means is I put 10 to the 9th down here, and I put 1 here. Okay, now I can see that that gram is going to cancel out. I will mark it out this way. Notice I went a different direction than I did before, and that should actually do it for me. Okay, now here's the trick. In converting, what I tell my students to do is multiply all the numerators and get a new numerator. Remember, numerator's on the top, and the denominator starts with a D, so it's down on the bottom, just in case you're rusty on that. So I'm going to multiply all the numerators. So 9.1 times 10 to the 4th times 10 to the negative 9 times 1 is 9.1 times 10 to the negative 5. And the only unit I have left is the teragram. Now that's my numerator. My denominator is 1 times 10 to the 9. So that's just 10 to the 9 down here. Now, you should remember that 10 to the 9 in the bottom is the same thing as 10 to the negative 9 up top. So now I'm going to get 9.1 times 10 to the negative 14 teragrams. So that's how you convert within the SI system. So if you're going from one side of the base to the other, it's customary, because it's easier to do, to just do a conversion from the one side to the base and then from the base to the other side. And that's what I showed you there. Does anybody have any questions on that? So go ahead.
I do have a question.
Yes, sir.
When you converted from 1 teragram to grams, it's 10 to the 9. Would that be 10 to the 9 or 10 to the 12 when you're doing that conversion?
Okay, so when you do teragrams, oh, thank you.
Okay. All right. I was confused.
Yeah, no, you did it right. You did it right. I forgot. I was doing a different one, evidently. I think I ended up doing, yeah, I did gigagrams. So yeah, you're absolutely right. Let me correct that. Thank you for catching me. That's the kind of help I need. So definitely keep up that. Don't worry about offending me. It's, me making a mistake is not a good thing. So yeah, it's 10 to the 12th. Thank you for that. Let me go ahead and erase it. And thank you again. That is 10 to the 12th, which means this on the bottom, instead of being 10 to the 9th, is in fact going to be 10 to the 12th. I might as well just do it like that. Ooh. So this is 10 to the 12 power. Thanks again for that. Now, instead of 10 to the negative 14, it's going to be, we had a negative 5 up top, and then we have a 12 on the bottom. That's going to become a negative 12 up top. So negative 12, 10 to the negative 12 times 10 to the negative 5 is 10 to the negative 17. Oops. So I'm going to write that now as negative 17 teragrams. So good job on catching me on that. And yes, that's exactly right. So does anybody have any questions other than why Mr. Younger's a goober? Maybe Mr. Younger should stop drinking before coming to class. I don't know. I'm not really drinking. This is tea. Anybody have any questions at all? Okay, some stuff I need to tell you about numbers in general. When you actually do, for instance, take a meter stick, hopefully you guys have done lab 1 now, which is introduction to lab, and you used a meter stick. And just to make sure we're all on the same page, I'm going to draw a little bit of a meter stick here. So let's draw a meter stick. I'm going to say it's basically like this. And really, a lot of meter sticks have the 0 be right here. If you're making a measurement and you're using that in, you're not being wise, okay? Because, I drop meter sticks all the time. Truth be known, I probably even chew on the end of a meter stick on occasion. So this end that's supposed to be 0 is not necessarily 0. So what we normally do for good practice in the lab, if you're using a meter stick or something like that, we either use a meter stick that doesn't have the 0 at the end. It actually has a black mark, and then there's a period of some wood or whatever, and then the end of the meter stick, or maybe there's aluminum on it. But the main thing is the 0 is separate from the end. Then you can use the 0. If the 0 is not separate from the end, you might want to start at either the 1 centimeter mark and measure from there and then subtract a centimeter, or start at the 10 centimeter mark, measure it, and then subtract 10 centimeters. That's one thing you need to know. Now, what I'm going to do is I'm going to draw what happens here. We have 1, 2, 3, 1, 2, 3, 4, and then there will be a long line, 6, 7, 8, 9, and then another long line that's even longer than the first, and that's supposed to be the 1 centimeter mark. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that's the 2 centimeter mark. And when you pick up a measuring device like a meter stick or a ruler or whatever, the first thing you want to do is try to figure out what the units they're using is. 3, 4, 5. And you do that by, if you picked up a meter stick, for instance, you could hold your finger, your index finger or your pinky, if you're a good sized guy like me, or even a good sized woman, who, in other words, tall. If you do that, what you'll see is a centimeter is about as wide as your fingernail. Wide as your fingernail, right? So if you did that, you would see that that distance from 1 to 2, for instance, is about a centimeter. So you then know that these numbers are centimeters. So that's one important thing. Another important thing is you got to look at the measuring device and see what 0 is. So in here, I actually marked the 0 as putting it at the end of the meter stick. When you're using vernier calipers, what you want to do is look for some line that says 0 to line up with some other line and then that would represent 0. It turns out when you close the calipers, that's where the 0 is, and you can look at what lines up with what to make sense of how you're going to use it. Now, that's two things you got to do. Figure out what the units are, figure out where the 0 is and what you're using to measure. And then the third thing is you want to find out what the divisions are between a number and the next number. In other words, what's a whole unit divided into? So again, I'm sticking with the idea of not using the n. So I'm going to start and see what the difference is between 1 and 2 on this meter stick. So what I'll do is I'll count the number of spaces, and I see I got 1 space, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means 2 to 1 is divided into 10 spaces. Notice they're equally spread. That's important. So what that means is each of those smallest marks our smallest division is equal to 1/10 of a centimeter, which is the same thing as 0.1 centimeters. And then you can verify that by checking and saying, okay, let's count them. So here's 1 when I'm to that mark, there's 2 when I'm at that mark, and 3 and 4 and 5. Notice the 5 is the one that's slightly longer. That's very typical. And then the 6, 7, 8, 9, and then of course here you're back up to 10. So yeah, clearly that's 1.1, 1.2, 1.3, 1.4, so on and so forth. So that confirms that your division by 10 was exactly right. So that's something you're supposed to do when you're dealing with measuring things. And then it's a matter of, hey, let's put this meter stick up against this thing and measure it. According to this, if you look at this meter stick right here, if you've got something that's really easy to measure, then you should be able to actually measure not to just 1 decimal place, but to 2 decimal places. Let me show you why. Let's say, for instance, I'm going to carry out a couple more of these lines, and I know these aren't perfectly drawn, but it's good enough for us to figure out what I'm doing. 1, 2, 3, 4, 5, 6, 7, 8, 9, and there's 4, and 1, 2, 3, 4, 5, 6, 7, 8, 9, and there's 5. So let's say I chose to measure this thing from 1 to whatever measurement, and it's really crystal clear, like it's a well-machined piece of aluminum or something like that, so it has a clear straight edge. So if I do that, what I will do is I'll draw it in hold on, my stupid phone is ringing. It aggravates me. What I'll do is I'm going to draw it in green so it stands out. I'm going to say I lined up the left-hand end of this thing perfectly with the 1. And then I'm going to say the right-hand end was here. And I'm trying to make this look like it's perfectly square and perfectly straight on this end. Okay, so let's say this little green thing is really what I'm planning on measuring. Let me see if I can clean that up a little bit. Oh, it's bad. Well, that looks worse too. Okay, so that looks pretty good. Okay, so what I do is I'm measuring from the 1, so I got to remember to subtract 1. Right now, the measurement looks like it's this would be 3.5 right here. This would be 3.6. This would be 3.7. This would be 3.8, right? Now, what you're measuring to is what line it's clearly passed. So I'm going to say this green thing this green thing is clearly, I would say 3.7 something, but remember we got to subtract the 1, so it's 2.7. Okay. Now that's just one decimal place, but I'm arguing that we should be able to measure this to 2 decimal places. So anybody tell me, does this number look like a good candidate for 3.79? Or excuse me, 2.79? Does that look like that measurement is about 2.79? Or maybe does it look more like it might be 2.71?
Probably 2 points.
Yeah, it does look like the 1 or maybe even a 2. But the main point I'm making here is clearly you can tell between 2.71 and 2.79. In fact, it could be 2.70, 1, 2, 3, 4, 5, 6, 7, 8, or 9. You might not be able to tell the difference between 2.71 and 2.72, but I suspect you could probably tell the difference between 2.73 and 2.71. You definitely could tell the difference between 2.74 and 2.71, and you certainly can tell the difference between 2.71 and 2.79. So really, we should be using 2 decimal places. Okay, so with that in mind, I would say that this measurement is going to be, erasing this real quick, I'm going to say this measurement appears to me to be about 2.71 centimeters. Now, you might look at this and say, that looks really like if I really tried to divide the space between 7 and 8, 3.7 and 3.8, if I really tried to divide that up in 10 equal intervals, this looks more like 2.72. Okay, some people might make that conclusion, and that's fine. That's the nature of measurements, is sometimes they're a little subjective. So if you were to record that, so what we would do in a lab type setting, we would say X is equal to some number plus or minus some error. That's really the way a lab result or a lab measurement should be recorded, is a number that you think is the best guess at what the number is, plus or minus what the error in it is. Okay. Now, when you have a number, you can always assume that the error is at least 1 in the last decimal place. In this case, it might be 1. So I'll say plus or minus 0.01, and then I'll put a centimeter after it. Okay. Now, if this thing wasn't so crisp and clear, clearly a straight edge that's exactly perpendicular to the ruler and therefore exactly perpendicular to the horizontal side, that makes it really easy to measure. So I think a 0.01 might not be that bad. That literally allows this measurement to reasonably be somewhere between 2.70 and 2.72. Which encompasses what I said some other student might have chosen as 2.72. So that's a reasonable thing. But in general, if someone tells you y is equal to 3.79 centimeters, then that automatically implies y is equal to at least 3.79 plus or minus 0.01. That's the smallest the error could be. Okay. In fact, if they explicitly told us something, we should write down explicitly what that error is. But if they gave me just 3.79, then I'm safe in assuming the error is at least 0.01. Does that make sense to everyone? Now, the important thing about that is notice that the 0.01 is in the exact same number place as the 9. And that's key because in the lab, you probably learned the sig fig rules. Hopefully you learned that in your lab today, and hopefully you already knew it, which are okay. And that's what a lot of freshman and sophomore level labs use. But in this class, we're actually going to learn of a thing called propagation of error, which is a calculus-based process whereby you can take a number X, which is given by some best value plus or minus some error. So I'm going to say this is the best estimate. And this is the error. And in fact, normally the best estimate would be what we call X bar, which means an average, or X inside of brackets, which also means an average. The error is normally supposed to be a standard error, which is not the same thing as standard deviation. In fact, standard error is related to the standard deviation by taking the standard deviation S and dividing it by the square root of the number of trials. Okay, we'll learn that in the subsequent lab, but I just want you to know that that's really how numbers should be written in a lab type setting. Now, what happens if you take X and you say X is 2.7, oops. X is 2.71 plus or minus 0.01 centimeters, and you say Y is equal to 3.79 plus or minus 0.01 centimeters, and then you say Z is 4.12 plus or minus 0.04 centimeters. If I want to calculate the volume's technically a function of X, Y, and Z, and turns out if it's a rectangular solid to be X times Y times Z. And what I mean by that is I'm only going to take that number in front of the plus or minus, which is called X bar, Y bar, and Z bar. That would be your best estimate of the volume. Okay. Now, what I'm talking about here is now that you've done that, how much error should that be? You can't even say, let's round it and then line up the error with that last digit because you don't have any way of rounding it. All you know is you're multiplying 2.71 times 3.79 times 4.12. And without the significant digit rule, you don't even understand that. But now that we supposedly know the significant digit rule, all three of those numbers have 3 sig figs. So according to the significant digit rule, when you multiply or divide two numbers, the answer should be rounded to the same number of sig figs as the number that had the least. All of these had 3, so we round it to 3 sig figs. Now, if you're going to use that number that you actually calculate, which in this case, let's go ahead and do it for the heck of it. Let's say 2.71 times 3.79 times 4.12. That gives me 42.316108 cubic centimeters. Okay. Now, according to sig fig rules, you're only supposed to have 3 sig figs, and hopefully your teacher taught you what sig figs were in your lab, but that would mean that this 1, this 6, this 1, this 0, and this 8 are not significant digits, are not sig figs. But the reason why I show you that is if you now need this volume to do some other calculation, then you should probably at least call it 42.32, or you might call it 42.316. In other words, you got to keep at least one extra digit to use that in subsequent calculations. And the way you can keep track of what digits are not significant is just like I did there. You just underline it. Okay. So as this goes, if I'm using sig figs, then sig figs implies V of X comma Y comma Z should be equal to 42.3 plus or minus I really can't do anything more than just call it a 1 in that last decimal place. So I'll say plus or minus 0.1 cubic centimeter. Okay. So that's something you need to understand. If someone gives you a number and it has 2 decimal places, then 1 in the second decimal place is the bare minimum error it can have. If they give you one with 4 decimal places, then a 1 in the 4th decimal place is the absolute smallest error it can have. Does that make sense? Okay, so that's what we're going to be using. All the labs you're going to be using sig figs and stuff like that. But usually by the second lab, your teacher might do it in a different order. By the second lab, I do a propagation of error lab where I teach you how to calculate that error. And I think you all can tell that the best estimate should really just be the average of all the trials. To be honest with you, if I want to raise it up a level to what you really would have to do, you might be the head of a company that has, 14 labs across the US do an experiment for you. And they actually calculate, the dimension of this block X. One lab might be stacked with nothing but fresh graduates from college, and therefore they don't know that much and they're going to make mistakes. Whereas one lab might actually have all ringers. Maybe that's a band of Nobel laureates in experimental physics that have been running your lab over there. So ideally what that means is some labs will have a lot of error and other labs will have very little error. And instead of just blindly taking a mean, you're not giving credit for the good labs and you're not taking away credit for the bad labs. So instead, what you do is you're going to use either the average or the weighted average. Okay, so what I mean by weighted, let's say your average error for your Nobel laureate lab is 0.002. Okay, so what that means is you take each of their X values that lab finds and you divide it by 0.002 squared. Okay, that would give you the fractional error. And what you want to do is you want that to have more weight. So if you divide by a small number, you get a big number. So that's why I said you would take that number and divide it by 0.02 squared. And then you take the numbers that the crappy lab gave you, maybe their error is 0.1, you divide that by 0.1 squared. And then, of course, when you're all done, you've got to figure out what is 0.02 squared under a 1. What is that value as a decimal? Do the same thing for the 0.1, the same thing for all the other errors. Add all those up and then divide by that quantity. That's how you do the weighted average. That's me just being completely truthful, letting you understand how the best estimate of a value is done. In our lab, we will never do that. Okay, we're always just going to use the average, but I want you to know that really a weighted average would be the gold standard if you really have good reason to believe some labs or some students, for instance, are better experimentalists than others. The way you do it is take and divide by either the actual error the lab has or the error squared, or you might try the error cubed. There's a lot of different ways you could do it, and all of those help. Okay. So does everybody understand what I mean by the best estimate is generally the average, but it could be the weighted average? Does that make sense to everyone? Okay, so that's really the way things will go. This whole semester, you're going to use sig figs in the lab. There might be a couple labs where we ask you to do the real error propagation stuff. That's completely up to your instructors. And ultimately, we're going to slowly transition all our labs to do all that and only that. We're not even going to use sig figs anymore, but we're not there yet. Okay. All right. So that's a little information about numbers. There is something called a fractional error. So I'll tell you what that is just in case. So fractional error. It actually has a very helpful symbol. The symbol for fractional error is sigma sub x over x. And I think you realize that sigma is the same standard error that I used up top. So if I look at my number X, what I mean is I'm going to take the 0.01 centimeters and I'm going to divide it by the best estimate, which is 2.71. In other words, this is X bar. Okay. So if I do that, I get 0.01 divided by 2.71, and the fractional error is 0.00369 and some other stuff. Okay, so that's a fractional error that comes in handy sometimes when you're using the propagation of error formulas. Generally, you don't use that number all by itself, but you use that number to multiply by the best estimate, and that'll give you the error in the V. So in other words, if you multiply, here's the formula again, sigma X over X is defined to be the uncertainty in X divided by X bar. So if I take sigma X over, or let's say sigma V over V, and I multiply that by V bar, then I just get sigma V, and that would be what goes right there. Okay. I know that's a little abstract given we're not actually doing measurements right now, but that's more than enough to get you started and have some understanding of what happens when we do our propagation of error lab. Your book literally talks about a fractional error and uses the word quadrature. It's about 2 paragraphs. So it's a little less than what I gave you. And that's why I gave you this. I'm really trying to give you an idea of what the error process really is in a scientific field. And the answer is you use statistics and you use means and averages or weighted averages to find the best estimates. And then you find the standard deviation, and then you divide the standard deviation by the square root of the number of trials, and that gives you the standard error. That's what's supposed to come after the plus or minus. If you actually then use that formula or that particular value of X or Y or Z in a formula, then you have to use propagation of error to figure out what your error is when you're done. Right now, we're just using round off methods using sig figs. All right. So now that I got that, I'm going to go back to doing some more unit conversions. Does anybody have any questions about that? If you look in my YouTube channel or in the links that I gave you in the module for week 1, you'll see that there's a video called, a link to a video called When Sig Figs Fail. So what I'm looking at right now is syllabus review, no sig figs, scientific notation and units. So that's the stuff I suggested you read. Introduction to SI, scientific notation, and standard ... That's not what I'm talking about. Here's a recap, the unit conversion multiplicative from my YouTube channel. That's another link that's in week 1 module. That's helping you do what I'm doing right here. It looks like I did give you a link for introduction, measurement, and estimating, and I gave you scientific method notation. I did not put in here, oh, there it is, sig figs and when they fail. So that's a nice little video, will explain and motivate what we're talking about. You can also read the introduction to error propagation that's listed in your in the lab section, which generally you don't have me for lab, so it's not relevant, but I leave it there because that topic is relevant. So feel free to read it if you want more background on this, because you will be learning it either next lab or sometime later in the semester. All right, no questions? Wow, I zoomed in and didn't realize I wasted a lot of space on my page. Now let's do another conversion, and the new conversion is something that I think is kind of funny. Specifically, my mother frequently would berate me and say that my mouth was running a mile a minute. Y'all probably all heard that phrase before, right? So let's use our techniques of unit conversion to figure out what a mile per minute is. So here we go. I'm going to say 1 mile per minute. And I'm going to remind you that the word per in mathematics means division. Okay, that one turned out really horrible. Oop, and there I erased everything back to it. So 1 mile per minute can also be written as 1 mile divided by 1 minute. Okay. What I would like to do is convert that to miles per hour, which you know in your car that says mph. Okay. So how do I do it? Remember, the trick with converting units is only multiply by 1. So I'm going to write 1 mile over 1 minute. And I'm going to put a multiplication symbol and a fraction bar there. And I want it in miles per hour. So do I need to change the mile?
No.
Yeah, because that's already in the right unit. But I do need to change the minute, don't I?
Yeah.
So since I need to change the minute on this fraction that I'm calling 1, should the minute be in the top or the bottom?
The top.
Exactly. So I'll put minute on top, and I know an equivalent statement for minutes and hours is 60 minutes is equal to 1 hour. Is that right to everybody? That seems reasonable.
Yes.
So now you can see the minute cancels out with the minute, and ultimately we get an answer of 60 miles per hour, which is equal to 60, which is equal to 60 mph. So that's what it means when someone tells you your mouth is running a mile a minute. Okay. I often use that figure, by the way, the fact that 60 miles per hour is a mile per minute. If I'm traveling, I'm always doing some sort of math in my head. It makes me a horrible driver. My wife is always picking on me about how bad a driver I am. I'm just a really fairly unattentive driver, often doing, you know, long division in my head and stuff like that. But like if I see a sign, maybe I'm going to Disney World and I see there's a sign that says Disney World 22 miles. I look down on my speedometer. If I'm in Florida, chances are I'm probably doing at least 70. They have sort of a way of just taking their interstate and let you do any speed. I will be sometimes driving 78 miles per hour down there, and people will just fly by me like I'm sitting still. But let's say I'm doing 70. I know 70 is bigger than 60 miles per hour. So if the sign says I'm 22 miles away, if I was going exactly 60 over that total period, it would take me 22 minutes to get there. So a rough estimate might be, okay, it's going to take about 20 minutes for me to get there, or maybe 21 minutes. And you could actually do the math to work it out. But that's kind of one of the things I use just as a first order approximation. Even 65 miles per hour all the way up to 70 is pretty close to 60 miles per hour. Okay. Now, what I also can do is I can string together a bunch of conversions. So right now, what I'm going to do is show you what 1 mile is, and I'm going to convert it to kilometers. So what I want to do, here's another example, convert 1 mile to kilometers. And I'll say exactly. The reason why I'm saying exactly is because you can look in your book, and what you will find is that 1 mile is equal to 1.609 kilometers. And that's sort of right, but it's not right. Okay. It's actually technically 1.609344 kilometers. And that's with the infinite number of zeros after it. So now that's what I'm going to show you. So I'm going to write 1 mile. And since I know I'm going to be doing some fractional mathematics, I'm going to go ahead and write 1 mile as a fraction. The way I'm going to do it is I'm going to say 1 mile divided by just plain number 1. Now I'm going to first use a conversion that I know is exactly right. So I happen to know that a mile is exactly how many feet? Anybody know that off the top of their head?
5,280.
Exactly. So by using that, I've converted it straight to feet to any number of decimal places. So if I put in 6,000 sig figs, then out pops 6,000 sig figs. So that's the beauty of it. Now, we have a relationship that Brandon just suggested was 1 mile is equal to 5,280 feet. Should I multiply by 5,280 feet per mile, or should I multiply by 1 mile per 5,280 feet? In other words, where's the feet go in the fraction and where did the mile go?
The mile goes
in the bottom.
Exactly. So the mile should be in the bottom. And yeah, you guys can speak up. You don't have to raise your hand or anything. If it gets too rambunctious, then I'll change that. But right now it's good. So 1 mile is in fact 5,280. And that's another symbol for foot. A single hash mark is a foot and a double hash mark is an inch. So now what we can see is I've canceled out the mile. Okay. Now I want to go from feet, which is what we have now. I'm going to go to inches because I know an exact conversion from feet to inches. What's that conversion? Anyone?
12.
Exactly. 1 foot is equal to 12 miles. Try to guess before I write it where I'm going to put the feet and the 12 and the 1 and the mile or and the inches and stuff like that. So I'm going to go ahead and write it. Now you hopefully have already thought about it. Okay. So now I can say that this unit cancels out with that unit, and I'm now in units of inches. Now here's the most important part. Switching from the British system, which literally Britain doesn't use, it's literally us and Liberia. Those are the 2 countries that still use the British system. And Liberia is like super, super small country, but we're stuck with it. So anyways, let's do this. I'm going to write another fraction. This is one you probably don't know off the top of your head, but I do, and I've known it for a long time, and it's exact. That's the beauty of it. And that is, in fact, that 1 inch is equal to 2.54 centimeters exactly. Okay, so I've used a swipe that goes from the bottom left to the top right, and I've used a swipe that goes from the top left to the bottom right. I'm going to go ahead and use an X this time. So I'll say this inch cancels out with that inch. And, this gives me a way to look back at my notes when I did a calculation and see if I made any mistakes, because I can tell exactly what thing canceled out with what. So now I'm all the way to centimeters. All I have to do to get to kilometers is now go from centimeters to meters and then go from meters to kilometers. So what I do know is that the conversion from centimeters to meters is that 100 centimeters is equal to 1 meter. And what I also know is that, notice this cancels out. So how are we going to do that? Well, I'm going to do another line, but this time I'm going to make it curved like that and that. Okay, so they canceled each other out. Now I'm up to meters. Now I'm going to convert from meters to kilometers. And what I know is that 1 meter is equal to, or excuse me, 1,000 meters is equal to 1 kilometer. So I've got to use a new hash mark. That means I'm going to start right here and do this. Start right here and do that. That canceled out. Now I can see that I, in fact, have only kilometers left. Life is good. And what I tell my students to do, just because everybody gets a little rusty from time to time on their fractions, is you multiply all the numerators first. So I'm going to do 1 times 5,280 times 12 times 2.54 times 1. And with that, I get 160934.4. Actually, I should make that a little bigger so you guys can even see it. So when I did that multiplication of the numerators, I got 1 point, or excuse me, not 1 point. I got 160934.4 kilometers divided by no units down here, but notice the denominator is 1 times 1 times 1 times 1 times 100 times 1,000. So that's 10 to the 5th, or you could just say 100,000 like that. When you carry out that division now that we've got the new numerator and the new denominator, I am going to actually divide the new numerator by the new denominator, and that gives me 1.609344 kilometers, and that's exactly right. I left off the meter here, or I erased it like a goober. Okay, so that's my final answer. And that's exactly true, meaning if I use that conversion factor and I have 8 decimal places for my distance measurement, then I can use this to give me 8 decimal places out. If I have 24 decimal places in the number I put in, then I can get 24 decimal places out because this figure is exact. Any questions on that? Okay. Holy crap, so much time. All right, so let me do a couple others. This one's really helpful. We can convert, for instance, miles per hour. Let's say 60 miles per hour is going to equal 60. Actually, let me not write it that way. It's going to equal 60 miles divided by 1 hour. Like that. And I want to convert it to meters per second and kilometers per hour. So let's say to kph and to meters per second. So I'll write 60 miles over 1 hour times what I just learned was that 1 mile is equal to 1.609344 kilometers. So I can do 60 times 1.609344, and that gives me 96.56 kph. And I'm going to underline these 2 digits because I wrote 60, which means I only have, at best, your book would call this ambiguous because there's a 6 followed by a 0. And that's what you're going to answer on questions in the practice tests and stuff like that, is 5,000 has an ambiguous number of sig figs. But if I put 5,000 with a dot after it, then it has 4 sig figs. Right now, I'm pretending to assume 60 means 2 sig figs. So I can get as many sig figs out as I put in. In this case, I only put in 2, so I have to call that 60 or 96.56. Technically, it's 96.56064. Okay, but that's our answer. 60 miles per hour is equal to 96, about 97 kilometers per hour. Now, if I want to convert 96.56 kilometers per 1 hour to meters per second, what I have to do is first realize that 1 kilometer is equal to 1,000 meters. And then I got to realize, you can do this in 2 steps, but some of you might already know that there's 3,600 seconds in an hour. I'm going to show it in 2 steps. I've already canceled out the kilometer. Now what I'm going to do is I'm going to put basically 1 hour is equal to 60 minutes. And then I'm going to put 1 minute is equal to 60 seconds. And you can see now that this, this hour cancels out with this hour, and then this minute cancels out with that minute, and that gives me 96.56 times 1,000. And then I'm going to divide it by 3,600. And I get 26.8224 meters per second. And again, that's technically with only 2 sig figs. So 60 miles per hour is equal to 26.8 meters per second. So that's another conversion. Any questions on that one?
I got a question. So why is it only 2 sig figs? Why wouldn't it be 4?
The 96.56 came from 60 miles per hour, which was only 2 sig figs. So I really, when I did that, I wrote it with the blue underlines in the blue box there. But when I wrote it here, I should have indicated that these two were not sig figs. So that's why it came out as 2. Okay.
Understood.
Okay.
Also, if it's an exact measurement, doesn't that change the sig figs that we use?
If it's, I don't want to say exact measurement because such a thing doesn't exist. All measurements have errors. Even if you use the highest technology, if you zoom in enough to say the edge of this desk, what you're going to notice is what looks like the edge is in fact a bunch of atoms and molecules jiggling. So you'd even have a large bit of error from that. So yeah, there's no exact measurement. But if you are using an exact figure like pi, and you use it to say 100 decimal places, then that would give you, in fact, 101 sig figs, and you can just write out the answer up to 101 sig figs, depending on how many you put in. Okay.
Okay, so you wouldn't use the sig figs if it were like a counting number.
Exactly. Yeah, that would be just a pure number that is understood to not have error.
Appreciate it.
No problem. What I'm going to do next time, we've ran out of time already, so class is really over. You're free to go. But what I'm going to do next time is I'm going to take the fact that the density of water, which is mass divided by volume, is 1 gram per cubic centimeter, and I'm going to convert that to kilograms per cubic meter, and I'm then going to convert it to kilograms per liter. The trick is realizing that a centimeter cubed literally means centimeter times centimeter times centimeter. So what you have to do is use 1 3 times, where 1 is 100 centimeters over 1 meter. And then you write it again, and then you write it again. And that's how you deal with the cube. So that's what we'll do next time, in addition to dimensional analysis. Sorry, I couldn't get more of that done. Like I said, the videos that I pointed out, that's more than enough to get you completely through all the homework, but I am going to move the homework and make it due on Tuesday at 11:59 instead of Sunday at 11:59. So you guys are free to go. Thanks for coming. I will post the video when it's done. Until then, I will see you on Monday. I'll wait for the last person to leave too, in case anybody has any question.
I got a couple of general questions. I swapped into your class yesterday, or excuse me, Monday. However, the Canvas didn't come through in time, so I wasn't able to attend your class because I didn't have a Zoom link.
Right.
I did go to the lab, however. Where can I find the Zoom link for last class?
Okay, let me stop sharing my screen and then start sharing it another way. I'm going to share now with this screen right here so I can show you that. So this is our Canvas page. And technically you guys meet on Monday and Wednesday. So this is actually your Zoom link. But what I put for the purpose of the Zoom link is this one right here. And that's not really a link. That's basically a document that is in fact an invite to the Zoom meeting. So it has the meeting ID and all that good stuff up there. That makes sense. What I do, and
yeah, that's how I found it. I mean, like,
go ahead.
The old posted videos
Mhm.
would be, where would that be?
Okay, so let me show you something else. I'm gonna switch this window to this. Are you looking at my YouTube channel now? You see that? Okay, so the class that you missed Monday is this one.
Okay, cover the syllabus. Oh, nice.
What I want to show you is, see down here, this little part where it says 241D02B.
Hey, that's me.
It says 08212023. So that's how you know, one, what class it is, it's 241, and two, what day it is. So that allows you to know what it was, when it was recorded and all that good stuff. But if you also go into my Google Docs, so let me kill this and go back to the other thing. If you go into my Google Docs, which is allowed right here, then you can click on my Google Drive. And if you want the actual notes that I just finished taking on my iPad, for instance, you can click in here and do a search for that date, the 08. I didn't use it, by the way. I didn't use the iPad that day, so there's no notes on Monday. But that's what you do for any of the other ones. You just look down in that little box on the YouTube video, and that'll tell you the name and date. And then you can use that to do a search in the Google Drive to find the notes.
Awesome. That's pretty cool.
Yeah, I just try to make that available to everybody. And when you take the 242, actually, this one says 242. Am I even on the wrong class like a dummy? Yeah, I'm looking at the wrong class, but yeah, but yeah, it's identical. That's why I didn't even notice it. The setup is identical for 241 and 242. So it's literally in the same order. There might be a slightly different file set there, but you do have the syllabus there as well as everything else.
Okay, and our homework is on there as well on Canvas.
Let me show you where the homework is. It's in Canvas, but technically it's in MyLab and Mastering, but you shouldn't try to go there except through Canvas. So this is actually your class, which is 241D02B. If you look down here in week 1 module, you'll see this is the homework and this is the conceptual homework. Both of those are due supposedly Sunday, but I'm going to move them back to Tuesday now.
Okay, cool.
So if you click on it, that's where you're going to be asked to sign up and all that good stuff.
I got you. Sign up for what?
The MyLab and Mastering. You actually, there's a code that you get when you buy the Binder Ready book at the bookstore, and that code allows you access to the website, the MyLab and Mastering, where the homework is. So when you click on this, you won't see all this stuff. What you're actually going to see is, now it's time to turn in your to create an account. So you'll create an account. They give you a 2-week grace period. So if you don't have the money right now, you can wait for 2 weeks, but you can still do your homework. And then at the end of that 2-week period, they lock you out until you either buy it or put in the code. And the code is, like I said, something that's sold with the book. You can also buy it there on the website, and it'll actually be a little cheaper usually.
Do you recommend that, or do I need to actually get the book from the bookstore?
No, it's in fact, the ebook is really all you need. Now, when you go to click on this and you want to try to buy it from the website, that's fine, but they're still advertising, even though they told me they're not selling it anymore. They're still advertising for $79.99 that you can get the MyLab and Mastering Physics without the e-text. Do not do that because you won't have a book. Okay. The other one's $129.99. And that one does come with the ebook. That's the one you need to use.
29. Okay, cool. And
I think that's still markedly cheaper than the bookstore, though.
Yeah, oh, I believe so. And just like taking the time to go down there and do it and all that.
Yeah, exactly.
Cool. I got one more question. Best way to contact you?
Okay. In my syllabus, I give you specifically my email address. So you'll see that. You can email me with that, and I guarantee you that I'm supposed to reply to you within 1 business day. If you watch that video for Monday, you'll see what I define as 1 business day. Also, when you see your syllabus, it defines it in there. If you don't hear from me at that time, then you're going to text me at my personal cell phone number, which is also in the syllabus.
Okay. Yeah, I sent you an email and I didn't get a reply, so I figured like not everyone is kind of stays up on emails, right?
Yeah, exactly. Did you send it before yesterday?
Yes.
Okay, then that's just me being a crackhead. I must have just missed it. But yeah, at the beginning of the semester, I have a lot of emails, so there's a good chance I missed all of them. But yeah, if you have a specific question, I didn't reply to you, so go ahead and text me.
It could have been yesterday. I don't know.
Right. It's all good. Just let me know if you need any help or anything like that. Do go ahead and at least get access to the site so you can access the textbook. If you like a physical copy of the textbook instead of having to read all the time on electronic, what I told students to do is buy that $129.99 package and then go find a fourth edition or even a third edition online. You can usually get that for a couple bucks, and it's really the text is about the same. The only thing that mostly changes is they catch a few errors and they change the problems at the end of the chapter.
Okay, that's a good idea.
Right.
Awesome. Well, I appreciate it. Thank you. Thank you so much.
No problem. Have a good one. Is it Eddie?
Yes, sir. Yes, sir.
Have a good one, Eddie.
You as well.